Operations class. Today I'm going to talk about the Jeffcott Rotor Model, and I'm going to begin with the history that led to its development. In 1869, Rankine was the first to analyze spinning shafts and concluded that at a certain speed, the whirl speed, beyond this point the shaft will radially deflect and increase without limit. This was fine to believe until in 1889 Laval ran a steam engine at a supercritical speed. In 1895, Dunkerley was studying vibration of shafts using weighted pulleys. He suggested that at a certain speed, called the critical speed, any shaft will bend and maybe break, but after this speed they run true. In 1916, Kerr said there's evidence to suggest there's a second, so the Royal Society at London sent Jeffcott to confirm. Jeffcott confirmed that there's a stable supercritical state and agrees with Foppel's thoughts of this at the time, and he added external damping to the situation. However, Jeffcott's rotor model wasn't practical enough for things such as aircraft gas turbines, and so a guy named Proll invented it around rotational structure versus stationary structure, and Proll and Miklostad together made transfer matrix method. So what is a Jeffcott rotor model? It's a flexible, massless shaft with a rigid disc mid-span spinning. Here on this diagram, you can see that G is the center of gravity, C is the center of rotation, E is the eccentricity of the system, which is the offset between the center of gravity and the center of rotation. Omega is the shaft spin speed, and V is the whirl frequency, which is the rate at which it spins around the bearing axis. So in a Jeffcott rotor model, there's three geometrical coordinates, which are x, y, and theta. However, when it's spinning at constant speed, only the transverse motion is looked at rather than the torsional motion. So there's 2 degrees of freedom, which produces 2 transverse natural frequencies equal to root k over m in 2 different orthogonal directions. And this allows the equations of motions to be solved independently on 2 different transverse planes. So there's 3 approaches to solving Jeffcott rotor models. And the first is to use sine and cosine terms with phase angles as the equation of motion. And this allows you to find the amplitude of x and y in these responses. The second approach is to use the whirl radius equal to x plus jy, and this ends up where the whirl amplitude over the eccentricity is in terms of the damping coefficient and the frequency ratio, which are really important for the response of the system. The frequency ratio compares omega to the natural frequency. A frequency ratio of greater than 1 shows that it's at a frequency greater than the natural frequency. The third approach to solving Jeffcott rotor models is using computer softwares to solve complex matrix systems. It's really important to note the importance of the frequency ratio and the damping coefficient on the response of the systems. If you of the response in this graph here, you can see that as zeta decreases, the amplitude at the critical frequency increases. And this critical frequency is the natural frequency, where the frequency ratio is 1. And you can see that lower than the natural frequency, the amplitude decreases, as well as above the natural frequency, the amplitude decreases. And if you look at the phase of the graphs, you see that with less damping coefficient, you have steeper transitions from 0 to 90 degrees as it approaches that natural frequency. And you can also note that damping coefficients greater than 1 stop at 90 degrees and never approach 180. However, underdamped responses approach 90 on the way to the natural frequency and approach 180 after the natural frequency. And what these suggest is that the damping is the most important parameter to reduce whirl amplitude at the critical speed. And the importance of the Jeffcott model is that it's a mathematical idealization. And though it doesn't reflect actual rotor dynamics, it allowed the solutions to complex equations in rotor dynamics, and the unraveling of a mystery that lasted for decades.